of all, 6033 the news. So this is the same news that Howie brought to us last time when we were talking about sort of low-level attacks. And so this is a relatively new attack that was discovered like just very recently. The reason I'm using it again is partly because it's still relevant, but also because I was able to find more details about it. So the attack is described in this paper, which we're not going to read in 033, but you have the title here. And the attack that they described is similar at a high level to the attack that you're going to see tomorrow. All right, so this will be a super good tie-in with tomorrow's recitation. The tie-in that I want to make with lecture is just to pull out some key things from this paper, knowing that I'm not going to describe the attack to you. What I went to look for this morning in this paper is some proposed, solutions in the paper, and they describe a few. And you can see a couple of them here. I've literally just, screenshotted them out. The highlighting is mine because all of the solutions that they are proposing to this particular attack that deals with a certain type of cache that many of us had never even heard of before, all of their proposed solutions have a negative effect on performance. And that is something that I want you to keep in mind for today, because that is something that we're going to see today as well. All right, so our lecture today, though, it's not about these styles of attacks. That's for you in recitation tomorrow. What we're going to do today in lecture is we're going to talk about sort of two different low-level exploits. So this lecture, even though it's all related, it does have kind of two distinct parts. All right, so the first one builds off what we were doing last time. All right, so last time we had a threat model where we were thinking about an adversary that had some level of access to our physical machine, and in particular could read some sensitive data stored in the machine. And it's worth thinking a little bit about, like, well, what type of adversary would have that access, right? A relatively straightforward example of that would be some sort of system administrator. And the reason I say that it's straightforward is not because I think, any of this is like straightforward or easy to understand, but when you have a system administrator, you have someone who is intended to have access to this type of data, right? If they can access this table, like, that is probably correct. That's a correct setting of permissions and things like that. But we still have to wrestle with the fact of, well, okay, we don't want a system administrator to just read off our username and password pairs. Like, we just don't want that, all right? And so we ended up with a scheme where we were salting hashes, and that's resilient to many, many different types of attacks. But today, I want to think about a little bit more about how an adversary that isn't intended to have access to this data might still get it. And this is something you're also going to be seeing something about this in tomorrow's recitation. All right, so we have data stored on this machine. How could an adversary access it? All right, so our threat model for most of today is an adversary that has the ability to run code on the machine, but not necessarily any particular privileges. Right? We're not thinking of a system administrator. We're not thinking of people with root access. We're just imagine, people that have sort of accounts on shared machines, which is a really common setup. All right, so I am going to show you in lecture a lot of different attacks that you can do on certain systems. Okay, so today in lecture, today I am not going to spend the entire time picking on Howie. Today I am the adversary. All right, so to talk about these styles of attacks, especially this first one, we need to talk a little bit about what the program stack is and how it works, right? Which maybe is not what you were expecting to happen to you today, right? So our program stack, a stack, is a basic data structure. The last object put on the stack is the first removed. So we push onto a stack, we pop off of the stack. The program stack in particular helps us deal with the following problem. It does many things for us, but here's a problem that we're concerned about with today. Right, I have a program, it's running, and it makes a function call. Right, that function goes off and executes, and when it's done, we need to get back to where we were originally. Right, we need to go back to the middle of that calling function and keep going. program stack allows this to work, right? And so in general, you'll see like program variables, program arguments, other data, those all get pushed onto the stack. We organize the stack into frames. You can think roughly a single frame represents the content that I need to run a particular function. And it's useful to organize the stack into frames because it makes it easier to do that return process. So let me show you an example. All right, so we're going to look, all of the code that you're going to see here is written in C or sort of C style pseudocode. I'm not expecting you all to know C. I'm certainly not expecting you to learn C from this lecture, but the fact that we are using C does matter here. So here is a fairly simple setup, right? We have a main function. That's the function that gets called first in C, right? So it declares an integer x, and then it calls this function, right, with the argument 7, right? And so imagine that that has happened, right? We're inside a function, and it doesn't matter what function does for this example. It can do whatever you want it to do, right? When we're inside of that function, the instruction pointer is pointing to whatever instruction in that function that we're executing. But when it ends, right, when I reach the end of this function, I need to be able to jump back to where we were in main. All right, so let's think about what's on the stack. All right, what does the stack look like? Oh, some people are asking in the chat about the slides. They may have come in late. If somebody could copy the links and put them back in the chat. The slides are up, just part of the website isn't refreshing fast enough for us. All right, so let's talk about the stack. What would we see on the stack? I'm going to explain all of this to you. All right, we will see local variables from main pushed onto the stack. We will also see, so that would be things like x, right? We'll see arguments to this function pushed onto the stack, right? So 7 in this case. This part here is something that we're going to be pretty interested in today. All right, this is the saved value of our base pointer, right? The current base pointer points to the base of the current stack frame, right? Once we finish executing that function, we'll be able to use this saved state to go back to where we were before, right? Similarly, we have a saved instruction pointer that lets us do the same thing, right? The current instruction pointer lets us point to whatever instruction we're currently doing. Once a function finishes, I want to go back to where we were before, right? And then we would have any variables needed to actually run function, right? So again, here's the important part to take away, right? This is the part that you need for this entire lecture. When we call a function, right, we save some state on the stack, right? That state is the saved base pointer and the saved instruction pointer. Then we go about executing the function. And when we're done, that saved state lets us go back to where we were before, right? That is what happens to allow you to call functions and to allow for that function to call another function, right? So this is what we're going to need to do today. Now, what we are going to do in lecture is we are going to exploit some things about this stack, right? So I'm going to show you some attacks that fall under the umbrella of stack smashing. All right, to do this, I need to do this for you on a really stripped down version of Linux that removes a lot of modern protections against this type of attack. So I'll talk to you at the end of this first part of the lecture about what those protections are and sort of why they're there and what the trade-offs are. I just want you to see what one can do. All right, so here we have this VM. You can tell that we're doing low-level attacks because it's just like a hacker, right? It's all gray and black, and we can't change any of that. So let me show you some code to start. This is the first thing that we're going to try to exploit. And this code is going to look frightening because it's all in C, but I am going to explain it to you. All right, so here's our first function. What does it do? All right, well, it's got a main function. That's what's going to get called. Notice that it doesn't have any other functions anywhere else. It's just main. It's going to allocate 2 variables, right? Modified and buffer. And you can see that I've put those on the stack there. Now, what are they? Modified is an integer, right? We don't really need to worry about that volatile keyword right there. It's an integer. And then this is something that if you are coming just from languages like Python, you're not used to seeing, right? This is a buffer that is meant to hold 64 characters, so 64 bytes. So the fun thing about C is that when you're programming in C, you are responsible for the majority of memory management. All right, so in this allocation, what the code has said is, give me 64 bytes of memory for me to store this buffer. Right, so when we run the code, we get 64 bytes of memory on the stack, reserved for that buffer. All right, the variable buffer points to the start of that memory. And then it is our job as programmers to make sure we don't overwrite things, right? And that's part of what's going to go wrong for us today. All right, so we've got these two variables allocated. We're setting modified, which is this integer, just to 0. And then we have this function, getS. All right, so get string. It's going to read a string in from user input and store it in buffer. This function is not recommended for use today, and you are going to see why. All right. Now, once we get through this, so again, all we've done, we've initialized two variables, we've set a number to 0, we've read a string in from user input. Now we have this kind of weird if statement. And I say that it's weird because it asks us to do something if this variable modified is not equal to 0. And if you look at the code, like look at code as just, normal people who write code, how would this ever happen? Right, I'm setting modified to 0. I'm not changing it anywhere here. When would it ever not be 0? Let's see what we can do. All right, so we're going to try something. So I have this code. This code is compiled for you, called stack0. And let me show you first how I'm going to run it. So I want to run it with a particular input, right? It's getting input from the user. I'll move this up a little bit so we can see. All right. So I'm going to run it this way. The first thing I'm going to use is I'm going to run Python on the command line. So this is something that you can do. So if I ran this, it's python-c and then some Python code, prints the letter A. The reason I am excited about this is because Python makes it really easy for us to make long strings, right? So if I want to print 64 characters worth of an A, there we go. All right, and I'm kind of excited about this because I want to see, I could use that as input to this program. All right, so here's how this might look. Okay, let's think about what happened. All right, I put in these 64 bytes. That was my input. Gets stored in this variable buffer. Buffer has 64 bytes allocated to it. I filled 64 bytes. I didn't overwrite anything else on the stack. Yeah, and I got this message, try again. All right. Now I'm going to try this. All right, you can answer in the chat if you want, or you can just think to yourself, what do you expect to happen? I've allocated 64 bytes for this buffer, and I'm going to try to put in 65 bytes. What might happen? Right, I'm just going to let you think to yourself, put it in the chat if you want, but we'll just stay quiet for like 10 seconds. Okay, we might try to overwrite something we shouldn't. It would also be a very reasonable thing to say, like, something should prevent this, right? Like the program should say, no, something happened, right? So let's see what we get. Indeed, we overwrite something. All right, so what happened here is that we wrote past the buffer and overwrote modified on the stack. All right, which again, if you've seen C before, it's fine. Just keep that excitement to yourself. If you've never programmed in C before or a language like C, this is surprising. All right, so again, getS from the chat. GetS reads in a string from input. So whatever string I input gets that string and stores it in buffer. Right? It does not come with protection. It does not check that I only put in a 64-byte string. It just says, well, I'm going to store it at the place the buffer points to. So what ends up happening is I overwrite this variable modified. Now, this is part 1 of 3, because as exciting as this is, we haven't done anything particularly interesting or useful or adversarial, right? I just overwrote a variable, right? Let's overwrite a more interesting variable. So I'm going to show you a second piece of code. It works similarly, all right? We're going to have the same idea, right? Oh, sorry, that was the adversary's goal. I should have added that before. All right, so it works similarly. I had to put the stack in a weird place so that I could still share this other window. We have two variables again. One of them is a string that's going to hold 64 bytes, right? One of them is this variable fp, right? We're setting it to 0, just like we set modified to 0 before. But here, this syntax probably looks odd. That's fine. fp is a function pointer, right? It's going to point to a particular address, right? And in theory, if that address points to a function, we'll be able to call that function. All right, so you can see from there what the code is doing. Reading a string from input. All right, so trying to get that string. This if fp, that's basically if fp is not 0, we're going to try to call the function that it's pointing to. All right, but again, if we're just looking at this from just straight looking at the code, fp set to 0, it's not changing. All right, so let's try our previous attack. All right, what happens? All right, again, we can do the sort of no attack version. This is stack 3. Nothing happens if I input a 64-byte string. It gets stored in buffer. Nothing gets overwritten. We're fine. All right. If I put in a 65-byte string, okay, now something exciting happened. All right, just like before, just like when I overwrote modified, here I end up overwriting this function pointer. Right, and so it attempts to jump to this address, right? This is basically just the hex representation of that character A. And you can see we get a segmentation fault. It crashes because there's nothing interesting at this address. It's not actually a function, so the whole thing just kind of breaks down. All right, so what if we tried to do this? We have this whole other function up here called win. What if we try to overwrite this function pointer with an actually meaningful address, right? One that points to this function win, right? Now we could try to do that. We could just we could try a bunch of addresses and see, see if we ever got a hit, right? That feels like the challenging part of this now, right? How do we know where win is stored, right? Well, we are going to know where win is stored because our computer is going to tell us. All right, so again, this is a very stripped down version of Linux. This isn't something that would work for you. Do not try this on your computers. It's not going to work, all right? But we're going to open this program in GDB. So GDB stands for the GNU debugger. It's a exciting command line tool that you get to use if you work with C a lot. So it is the debugger for C code. And GDB tells you all sorts of things about the code that you're trying to run, right? This is not a lecture where I'm expecting you to learn GDB. You don't have to remember these commands, don't worry. The important thing is that you understand what one can do. And one can just ask, okay, where is win? Where is this function? All right, and this number that we get right here, this address, it's where it's stored. All right, so let's try to use that information. All right, here's what we know now. We know how to overwrite function pointer. We know the address of win. Let's see if we can put it in. All right, so forgive me while I have to type this very long thing. All right, so I'm gonna do 64 bytes and then past that, I wanna add the address of this function. This is where my typing gets very bad. Okay, so this is the format in which we put an address. And this is not gonna work right away. All right, so let's see what happens. All right, so you say, okay, we got that print statement. We overwrote the function pointer, but it tried to jump to this address, right? 2484.48, which is not what we put in. It's because we put the address in the wrong byte order for this architecture. So we can fix that through some more Typing mistakes on my part. Okay, so if this works, what should print on the screen? Tell me in the chat, what should print if we get this to work? Yeah, it should print code flow successfully changed, because if this works, we've overwritten the function pointer, it gets called, and we're hoping that it calls win. Okay, so let's see. Yay. All right, we did it. Okay, now first, again, this lecture involves a lot of detailed typing on my part, a lot of stuff in C that you haven't seen, a lot of stuff in GDB that you haven't seen. That's okay. That's not the point of this lecture, right? But the point, the high level point that you should take away from this is surprising, right? This code over here does not call the function win. And yet we just got win to execute just by running this code, right? That's wild. Now, we're going to go one step further. The reason we were able to do this attack is because we just got lucky. We had this function pointer available to us. The code called a function pointer, right? It called this function. What if we didn't have that sort of attack vector open to us, right? What if instead, this is going to be much, much simpler code, right? What if we only had this, right? This in some ways looks like the least attackable code, right? It's declaring our buffer, just as always. We're reading it in from input, right? Get S, again, it's reading from input, just like input in Python. We have this function here, but it's not getting called in main, right? Win isn't getting called in main. There's no function pointer, nothing is getting called here, right? And yet we're still going to be able to get win to execute, right? What we are going to attempt to do to make this work is overwrite a different part of our stack. We're going to try to overwrite this saved instruction pointer, right? This is the thing I introduced to you at the beginning. Remember what this saved instruction pointer and saved base pointer are meant to do for us. When we are about to exit a function, we have this saved state, right? Save base pointer, save instruction pointer. That tells us how to return, right? It tells us where to go. All right, so what I'm going to try to do is make this saved instruction pointer point into win. All right, so that we end up executing this code, even though at no point here is the source code actually calling a function. All right, so this is going to be a little bit more complicated. We're going to need to do a little bit more work. Again, I'm not expecting you to remember exactly what I'm about to type in GDB. I'll put it all in the notes for you if you want. What I want you to see is that this is possible and not that hard in this early version of Linux that we're working with. All right, so before I do that, let me just remind us of what we're trying to do. All right, we want to overwrite this saved function pointer. Oh, come on, window. Okay, so first thing we're going to do, I am tired of typing 64As all the time. So I'm going to set us up with what we'll call a payload. All right, so this is my 64As that I've been using them. I'm just going to save them to a file, right? /temp/payload. So that payload, it's literally, if you opened it and read it, it's 64As. The reason I'm doing that, it's not just because I'm tired of typing. It's going to make it easier for us to learn some things about this code through the magic of the GNU debugger. All right, so let's do that. This code on my machine is called stack4. All right, so we're going to open it. And we can do some of the same stuff that we did before, right? It's important. This is a new piece of code. We're still going to want to know where this function win is located, right? And you can see this is the address of win, right? That's the address that we're going to try to overwrite on the saved instruction pointer, right? But to make sure that we know exactly where to write, because there honestly might be a little bit more saved state here. We want to know exactly how far past buffer do we have to write to find it, All right, so let's do this. You all, I'm sure, have fond memories from 004 of looking at assembly code, right? Is that correct? Fond memories? Yeah, thank you, Johnny. Yes, I think we've all enjoyed as people the time we spent with assembly code. Um, Enrique, this is the only assembly code I'm going to show you today, but it's cool to know that you can get it. Right, so we're going to disassemble this main function. Okay, this is what main looks like in assembly. All right, you can see it doing things that you would expect. Pushing base pointers onto the stack, setting base pointers, things like that, doing all sorts of cool stuff. We don't need to worry about all of the details of assembly. That's fine. Enrique, you're fine. You're not going to have to look at this again. But what I want to do, I want to set a breakpoint, right? A breakpoint in a debugger stops the code at that point. I'm going to set a breakpoint in a very specific place. I'm going to set a breakpoint like right here, right on the second to last line when we're about to exit the function. All right, so GDB does this. GDB is particularly good for this. Yeah, okay. So you can see I'm setting this address, right? So I've set that breakpoint. Everything is good. So I'm going to run the code and it's going to stop here, right? It's going to stop right before it exits main, right? And we're going to look at a couple of things. So runs the code, and I can run it with this input that I had before. That's, again, that payload that I set up, 64 bytes. We're not trying to overflow anything right now. We're just trying to learn more about this code. All right, so I run it and you can see it hits this breakpoint. All right, now let's look at some things. All right, we can look at the current value of our base pointer. This syntax is going to look wild. All right, but that's okay. All right, what this is asking for is X is asking for a particular memory to read from a memory location. We want 2 bytes of memory, and I want it to be output in hex. That's just a fun syntax we have here. All right, so what do we see here? All right, what are we looking at? What we're looking at here is, so we're asking for the current value of the base pointer, all right, just pointing right before the stuff that I've saved, that's saved state, right? And you can see it. This is our saved base pointer. This is our saved instruction pointer, right? That is what those values are, right? So base pointer, previous base pointer was B, FFFF, DA8, all right? Now, I would like to know where those live on the stack, right? I'd like to know in particular, where are they in relation to my saved buffer? Just in case there's anything else happening between here, or if the stack was allocated in a little bit of a more exciting way than I've described, we can do that too, right? We're just gonna ask for a little bit more memory. Again, not expecting you, the syntax of these commands is fine. We don't need them, right? You don't need them, I need them as the adversary. You all are non-adversarial today, right? I'm gonna look at the current stack, right? And so what are we looking at here, right? This looks wild, this looks like a bunch of hex, but this should be familiar to you. All of these 4 1s, 4 1, 4 1, 4 1, 4 1, that's our buffer, right? 4 1 again is an A, so we're seeing all of these A's, right? So that's our saved buffer. You can see there's a couple of things happening right after buffer. And then here we have our saved base pointer. We know that's the saved base pointer because we asked for it before. We have our saved instruction pointer. We know it's a saved instruction pointer because we asked for it before. If I had just looked at this without knowing this, I wouldn't really know what was what here. All right, so how am I going to use this? What does this tell me? And well, this tells me if I want to overwrite that saved instruction pointer, I've got my buffer stored here, and then I've got to go, this is 4 bytes, 8 bytes, 12 bytes beyond that to overwrite the instruction pointer, right? That's where it's saved. Okay, again, it doesn't matter why it happens to be 12 bytes past it for this example. It just matters that we can find this out and it wasn't that hard. All right. No, yes, I don't care. All right, so let's see it. Let's see it happen. This is the crowning achievement for us currently, right? So 76 A's, my original 64 A's, plus 12 more A's. All right, and then What am I going to put in here? I'm going to do the address of win, which we got way before. All right, backwards. Let's see what happens. Amazing. All right, code flows successfully changed. We were able to jump into this win function. We did get a segmentation fault after that. It was because once win finished, there was kind of nowhere to go, right? But we did get to execute this function, right? And again, I want to stress all of the details of what I typed here. That's not what I want you to take away from this lecture. What I want you to take away is that if we look at this code, there is no reason to suspect that this function would ever have executed. And yet, there it was, right? Now, those are the basics, all right? But really all I did here was get the code to jump into an existing function, right? The next step, if I was a real adversary, the next step would be to insert my own code onto the stack, right? We're not going to do it in class because of time constraints, but the approach is basically the same. It's not much more complicated than what I just showed you, right? In particular, my goal would be to write code that executes a shell, because once I have access to a shell on this machine, I can cause all sorts of trouble, right? Now, I told you all I was doing all of this on not a modern version of Linux. It's because modern Linux has all sorts of protections against this. In fact, if you try to do the most basic one, where you overwrite a variable on the stack or overwrite the instruction pointer and things like that, not only will C compilers tell you you should not be using the function getS, you'll see messages that say stack smashing detected, right? So what are some of these protections like, right? Well, the things that make these attacks possible is our ability to predict memory locations, and eventually our ability to execute our own code on the stack, right? That's what would let me do sort of the next step of this, where I try to execute a shell. All right, so some of the protections that exist in modern Linux are having a stack that isn't executable, right? You just straight up can't execute code on the stack. And there's also all sorts of address space layout randomization, which is exactly what it sounds like. It is much harder to predict where particular key places of data are going to be. It'll change from run to run, right? That is not the case in the code that I just showed you on the version of Linux that I just showed you. All right, so all of that is good, but there are counterattacks to these, right? We won't go into the details, but I want you to get a sense, all right? Some attacks work by exploiting just some of the shared libraries that exist for Unix. So libc is one of these libraries. libc defines system calls. It lives in memory. It can be accessed by all programs. You want that. You want programs to be able to access libc. And it's typically at a fixed location in memory. So there are a lot of exploits that work by trying to execute a command in libc and getting a shell, right? That's what an arc injection, or not injection, or return to libc attack does, right? There are other things. For instance, what if we took our program stack and we said, oh, okay, wait, I was saving the base pointer and the instruction pointer on the stack, and the adversary is overwriting them. What if I say I save them on the stack, but then I also save them on the heap, and I could check whether they're equal, so I could detect any rewriting. It would have some performance implications, but maybe that's worth it. You can smash the heap as well, right? It works slightly differently, but you can do that too. So maybe you think, okay, what if we could just prevent overwriting the return address in some other way, right? Like, do all buffer overflows require overwriting the return address? They don't. There are all sorts of other exploits doing things like trying to overwrite function pointers, like I showed you. There's all of these solutions, but then sort of these counterattacks that come up, right? And especially, if you're a person who has experience with languages other than C, you may be thinking, there's almost an obvious solution here. Why don't we just check bounds, right? Why doesn't some part of this system check that I'm not writing past the end of buffer, right? That's how I got into this problem, right? You've probably experienced that type of checking, like in a language like Java or something like that. C doesn't do that, right? A reason, right, it doesn't do that, bounds checking is pretty expensive, right? Many people love C for the ability to write compact code that results in really compact assembly, right? Adding bound checking can result in orders of magnitude more instructions. So just as an example, this is some network style code in C, some like network input output stuff. Does not matter to us what it does. What matters to us is it's quite short. It's like 9 legit lines, technically 10, right? In Java, we end up with like hundreds of lines to do this, right? And also, no one was really thinking about security when they were designing C, right? So some key points to take away from this first part of the lecture, right? We see all sorts of low-level style of attacks that make it possible for adversaries to read data that we didn't give them permission to read, right? There are solutions to those attacks. And then there are counterattacks, all right? We're gonna try to become more comfortable with that by the end of this lecture. But we have one more thing to do first. All right, so as long as we are like in it, right? We're in a single machine, we should talk about compilers, right? Why not? What does a compiler do? All right, compiler's job is to take source code, compile it, and give us machine code. All right, that's what a compiler does. We're still going to be thinking about C here, so I want you to envision a C compiler. Right now, this C compiler, of course, like we had to write the compiler. Right, so there is source for a C compiler. Right, you can look at the source code for a compiler. When you actually go to use the compiler, it's like an executable, right? It's like a binary, it's machine code. You input a source, you get the machine code for that source. All right. Now, what's kind of interesting about this diagram is, well, I got this machine code for this compiler. Something must have compiled it, right? And in fact, in the case of C and other languages, the C compiler can compile itself, right? This is a common exercise in compilers, right? So this is how we start to build C binaries, right? So the C compiler source is in C, the compiler binary is in C, right? This is all fine. This is not a class on compilers. We're not going to worry about the ins and outs of these compilers. We're going to think about, suppose we wanted to be a little bit insidious, right? So we've got this C compiler hanging around. Unix is written in C. If you use a C compiler, it's a compiler, compile Unix. All right, now let's say, okay, so again, I'm the adversary today. Karen, you're going to be the non-adversary. Okay, so yes, you're trying to detect all of the bad things that I'm doing. So here's a bad thing that I want to do. I want to add a backdoor to Unix. And what that means is I want to insert some code into Unix that basically says, username Katrina can always log in. All right, or whatever other hack, but like that seems as good as any. So here's something I could try. All right, I just like hack the Unix source. We compile it, and then we would get this binary. Right now, imagine people trying to detect this. Specifically, imagine Karen trying to detect this. All right, Karen is an experienced computer scientist. She knows what I'm up to. Right, Karen is not going to fall for this at all because she's going to look at the source. Like she's going to be like, Katrina, you gave me this exciting new Unix source to compile, but I'm reading it and there's literally a line that says, if user equals Katrina, then let in. Okay. If we're looking at source code that is hacked in some way, I don't love the word hacked, but I'm going to use the word hacked here. That's hacked in some way, we just read the source code. Okay. So Karen's smart. I'm also smart. Here's how smart I'm going to get. I'm not going to hack the source code. I'm going to hack the compiler. Right? And the way that I hack the compiler is to say, okay, compiler, do all the stuff you would normally do. When you are compiling Unix, when you recognize that the source that you are compiling is the Unix source, add in machine code that inserts this backdoor. All right, that's sneaky, right? Sneaky because, you know, when I hand Karen this Unix source, I'm gonna say, hey, Karen, here's this source. And look, I also brought you this compiler to use. You know, she's gonna look at the source and say, well, okay, the source, you know, the source looks good. But again, she knows what I'm up to. She's gonna say, Katrina, give me the code for your compiler. She's gonna look at the code for the compiler and say, ah, I see you're doing it again. You're trying to insert this backdoor. Okay, so what if I lie? All right, I'm very adversarial. What if I lie? And I just say, oh, Karen, here's the compiler source code that I have for you. Here's the Unix source code for you. They are pristine. And also, look, I've already compiled the compiler for you. Just go ahead and use it, right? All right, so what can Karen do now? All right, can she tell that I'm lying? It's easy for Karen to read source code. No one wants to read machine code. Like, machine code is basically zeros and ones. That could take ages, right? But here's something that Karen could do. All right, Karen is going to be able to detect this. All right, Karen's going to know that I'm lying. And here's how she's going to know. She's going to say, okay, Katrina. She would be that exasperated with me at this point. She's going to take this compiler source that I'm claiming I used. She's going to recompile it. All right, she'll even compile it with, you know, this hacked binary that I've given her. All right, and you know, she will just get a clean C compiler, because the only thing I've done to this in this hack is saying, okay, if you're compiling Unix, put in this vector. All right, and then she's going to take her new compiler, take that Unix source that I gave her. She's going to get a clean version of Unix, and then she's going to say, Katrina, these do not match, right? This Unix source that you gave me is clearly hacked, right? I've now created brand new, clean Unix machine code. I know that you are trying to trick me into this backdoor, right? We go through this every year, Katrina. I'm so tired of it. Okay, so yeah, Karen can detect that I was lying. All right, I'm going to update our little key fact. Right, not only is it easy to detect hacks in source code, it's easy to detect this hacked compiler. Right, Karen just recompiles things and then she can do like a diff. All right, so Karen's doing great so far. All right, but we still have 5 minutes left. We're going to keep our setup, right? This is the setup. We had all of this clean source code. We had these hacked compilers that I've given to Karen, and I'm gonna get better or worse depending on your ethical standpoint in this lecture. Version 2.0. Now my hacked compiler does the following. If it detects Unix, it inserts a vector. If it detects that it's compiling the C compiler, it inserts backdoor inserting code to C compiler. So basically it says, okay, if this input is Unix, in output, add some machine code that inserts that vector. If this input is a C compiler, in the output, add in the machine code that makes this a hacked C compiler. So here's what's going to happen when Karen tries to do the same thing. All right, she runs the Unix source code through this hacked C compiler. She get a hacked source, right? That's the source I'm trying to get Karen to use. I really want to have an account on Karen's machine. All right, well, she can take her clean C source code, run it through this new hacked compiler, and now she doesn't get a clean C compiler, right? Now she gets a hacked C compiler because my compiler said, hey, I'm compiling the C compiler. I'm gonna make it have this backdoor inserting code. So when she tries to use it to compile the Unix source, she gets this hacked source. And now that test that she did before is not going to show a lie. All right. So this is wild. This is kind of a wild attack. And you might think, well, this is just maybe seems like a creative thing for Katrina to have done during a lecture. All right. So this is a relatively famous attack. And this attack comes to us from Ken Thompson. So you know Ken Thompson. He developed Unix. He was one of the authors on the Unix paper that you read, and he won the Turing Award, which is a very big deal in computer science. In his acceptance speech, he described this attack, right? And he indicated that he had perhaps inserted this attack into versions of Unix, right? And part of the moral of that story is that Ken Thompson is telling us, well, you can't trust code that you did not totally create yourself, right? If you have source that you wrote yourself, did you write the compiler, right? If you also wrote the compiler, did you build the hardware that you're running it on, right? So that was part of the point here. But there's a couple of other important points from this this paper, which was actually his acceptance speech when he won the Turing Award. One of the points that he makes in the paper is that one of the ways to deal with this sort of, attack landscape where you can't trust anyone and there's always new attacks is through policy. So one of the statements that he makes is the act of breaking into a computer system has to have the same social stigma as breaking into a neighbor's house. It should not matter if the neighbor's door is unlocked, right? So you can agree or disagree with that statement, but notice that he's pushing for policy changes, not technical changes, right? The other interesting fact about this paper, it has only 4 references. And at the time, there was this one Air Force document that they couldn't find a full citation on, but we know what it is now, right? So it is this document. The reason that I'm bringing this up to you, so one of the things cited in this speech, P.A. Carter was a student in 6033, and R.R. Shell was also a student in the seminar that kicked off the development of this class. This class has been around for a while. This class predates me. It predates almost everyone on this Zoom call, right? So this is the end of a terrifying lecture in many ways, right? I want to be clear though, between today's lecture and tomorrow's recitation, you should not be scared away from computers forever, right? There are, like, low-level attacks can be insidious, right? But we can make progress, all right? As we develop solutions, attacks get more sophisticated, it's true. A lot of times though, they get harder to mount, right? They might take more time, they might take a specific style of access. Some cases it might not be worth the effort, right? Like imagine when we were doing passwords, right? Eventually it was just too time consuming, right? For Howie to figure out all of these hashes, right? And then again, one of the most important things I think from this paper is that yes, even if you maybe can't trust code that you didn't write yourself, there are solutions beyond technology that we can think about, right? So that is the end of today's lecture. Again, you don't have to read assembly code, all right? I want you to understand the basics of the stack smashing attacks, but all of the commands that I wrote for you in GDB, those are not things that you need to walk away knowing. Okay, so end of lecture. Let me stop sharing. Let me stop recording.